Thank you very much. And thank you for coming on the morning after the conference dinner. I know it's always a struggle to get up. Today I'll be talking about a problem motivated by my postdoc work in Oxford, which is with Ian Hewitt. He's my postdoc supervisor. And it's about these problems in glacial hydrology, which is basically the problem about how water, like meltwater, say, flows either over or through or underneath glaciers, and it affects how the glacier itself evolves in time. But my background is in more fundamental fluid mechanics and free boundary problems, and so Ian's been graciously enough to let me do some of these problems as well as the more modeling aspects of glacial hydrology. Okay, so first I'll start with the motivation, and then I'll get to the actual maths of it. And I apologize to any of the analysis people in the room. It's going to be a very applied talk. So you can ask me about existence and uniqueness at the end if you want, but I won't have an answer for you. Okay, so this is Glaciology 101, if you like. If you're from Australia like me, and your normal experience of ice is on like this scale of little cubes in your drink, you normally think of ice as a solid, right? It's the only evolution it does is it melts very quickly if you're in Queensland. But if you're on the scale of a glacier, and this is a glacier in northern Greenland, I think, called Elephant Foot Glacier for obvious reasons, then it actually acts more like a viscous fluid because you're on a much larger time scale and also a much larger scale of pressure and mass and things like that as well. So starting working in the 1950s by John Glenn and also many subsequent laboratory and observational studies, ice on a glacier scale is normally modeled as a viscous dominated, so Stokes flow, shear thinning fluid. What happened?
Yeah,
Seem to
it
die.
comes back if, okay, I think it's might be a problem. Here you go.
Okay, well, very good. So you have, if sigma is your stress tensor, then the divergence of the stress tensor is 0, that's the Stokes flow. And your stress tensor itself has a pressure part, and the deviatoric part, or the viscous part, is a power of your strain rate tensor D, as opposed to just being proportional to D, which it would be if it was a Newtonian flow. And that power is normally taken to be about a third, so it's a significantly shear thinning flow. And you can tell already in this sort of picture that there's going to be free boundary problems involved in the flow of ice. In this case, it's just, if you like, a blob of ice moving out, but that boundary would be a free boundary. But we're more interested in boundaries between ice and water, so more glacial hydrology. And there's a couple of important places where this occurs. Firstly, there's in the glacier itself. For instance, you could have water melting on top of the glacier during the summer, or it could be rainfall. It'll flow through the glacier because it's more dense, and then it'll flow out of the glacier to wherever the glacier ends, either on land or into the ocean or into a fjord or something. And that's normally called glacial hydrology. That's the hydrology of the glacier itself. And there's also the interactions between the glacier and the ocean, or a fjord, say, where it ends. And this is a bit of a more complicated problem because it involves not just the salty ocean water and the glacier itself, but it also involves the fresh meltwater. So you've got mixing of less dense, colder fresh water with warmer salty water. You get buoyant plumes and things like that. And that sort of thing controls, or certainly strongly influences, how a glacier melts at the end. So that's a very important problem with regards to stability of ice shelves or glacier fronts or things like that. And that's actually something that we're working on now, but for the purpose of this talk, I'm just going to talk about a very specific problem here under the glacier, in particular to do with these channels of water that end up cutting their way through the ice. So here's some pictures of these channels, or pictures of what you could imagine these channels would look like. And there's kind of a balance between two different forces with regards to these channels. Firstly, there's the inward creep of the ice, because you're thinking of it as a very slowly flowing viscous fluid, which is wanting to close up these channels. But the water flowing through them is also melting them, right? So you kind of have this dynamic equilibrium between the two effects. And the mathematical modeling of this was first really put together by Hans Wesselsberger in the 1970s, where you assume you have a circular channel for simplicity, or you assume you have a semicircular channel at the bottom, and then you mirror it over, assuming there's no stress between the glacier bed and the bedrock underneath, which itself is an assumption which has seen a lot of work done on. And this lets you solve the ice flow, so that non-Newtonian Stokes flow exactly. So that's this blue term here. If S naught is the radius of this circular channel, you get a closure term due to the ice flow, and then you get some sort of opening term due to the melt rate. And because this is normally just one equation in a much bigger system of equations with regards to how the channel size and the pressure and the flux of the water evolve, normally that melt rate comes from pretending this thing's like a pipe. If you're an engineer, you have a formula for the viscous dissipation, I suppose, of heat due to turbulent flow in a pipe. And these channels are like order meters big, so the water flow through them is certainly turbulent. But in practice, these things are not necessarily circular, right? And studies with regards to what happens when they're not circular are not nearly as common, because then you no longer have an exact solution for that non-Newtonian Stokes flow for the ice. There's been some finite element studies. This is a paper by Paul Cutler in the late 90s, I think. And some of his findings were the fact that the aspect ratio decreases as it contracts. In other words, it becomes more elongated, it becomes longer and flatter. And also that the rate of contraction increases when you don't assume that it's just a circle. So if you like, that's glacial hydrology 101. What I want to connect this to is a classical problem in free boundary problems with regards to two-dimensional Stokes flow around a bubble. Because you can see this is going to be a very closely connected problem. Major difference is this is about Newtonian Stokes flow. So pretending we have Newtonian ice, so instead of that shear thinning rheology, we have Newtonian rheology. You can actually write down many exact solutions to this problem when your boundary is not a circle, right? And this utilizes the relationship between solutions to the biharmonic equation. So if you're doing Newtonian Stokes flow, you can model, or you can write down your equations in terms of an area stress function or a stream function, which satisfies the biharmonic equation. And then you have no stress boundary conditions on your free boundary, and a kinematic condition as well. And then you'd have some far field condition corresponding to a constant pressure, say. But because if you have a solution to the biharmonic equation, you can write it using its Gauss-out representation in terms of complex analytic functions, you can actually write down exact solutions, many classes of exact solutions to this problem where this boundary is not a circle. And these normally take the forms of conformal mappings, since you're using complex variables from the unit disk, say, in an auxiliary variable, to the fluid region, which in this case is the ice outside there. So we're not considering the melt rate yet. This is just this classical problem from 2D Stokes flow. Some examples of these non-circular exact solutions. One of the most simple is if you have a Joukowsky type transformation, which turns a circle into an ellipse. So here Z is my physical variable and zeta is my auxiliary variable, where my fluid region is just the disk. And this is a time-dependent conformal map. If you didn't have that second term there, so if epsilon was 0, this would just map a circle to a circle, and that would be this exact solution, which is just a contracting circle. And it's non-dimensionalized here, but you can see the basic idea is that it contracts for a given constant pressure of infinity. It just contracts exponentially, but never closes in finite time. If you add on this extra term in the conformal mapping, this makes it an ellipse with a non-unity eccentricity. And in this case, it contracts, and it does shrink to a line in this case in finite time. In fact, it shrinks in such a way that the focal points of the ellipse, which if you like are the ends of these two ends of this red line, remain fixed over time. This is one example of an exact solution, and it's kind of related to those things, or that phenomena that Cutler saw in his paper with regards to the non-Newtonian Stokes flow that he could only solve numerically. The problem with this, of course, is you can come up with more exact solutions which have some very other interesting behaviors. If you have a higher power of zeta, if you add it onto your exact circular solution, then you can end up with solutions that evolve over time and form cusps. So if you like, it's an unstable problem in a way, this contracting circle. It ends up folding in on itself and forming cusps. And from a complex analytic point of view, these cusps correspond to critical points of this mapping function, of which there are k, hitting the circle in a finite time. So if you like, the conformal map breaks down, and that corresponds geometrically to the formation of cusps. So there's kind of an instability in this problem for Newtonian Stokes flow. And as well as this being an exact solution, you could also kind of think of this as the linear stability result. If epsilon is really small, this is equivalent to a kth mode sinusoidal perturbation of a circle. And this basically says, because this term is growing exponentially at the same rate that the linear order is contracting exponentially, that the circle is unstable to all modes of perturbation, and that rate of instability is the same for all modes, which is a very interesting fact in itself. So if we want to take this theory of 2D Stokes flow and kind of try and apply it to the problem of the channel in the ice, it's kind of two questions that arise. Firstly, there's how does that interior melting affect this folding type instability you see in 2D Stokes flow? And secondly, is this instability we see in Newtonian Stokes flow carry over to non-Newtonian Stokes flow? Okay, well, let's start with melting. Melting's a bit of a challenge because when you had a perfect circle, it didn't really matter how you thought of melting occurring, because in terms of the distribution around the boundary, it could only do one thing, right? It has to be uniform around the boundaries so that it stays a circle over time. But when we no longer have a circle, how this melting is distributed matters, right? It'll change what shape my non-circular boundary evolves to over time. So I'm going to talk about two very simplified models of melting, one of which is not very realistic, and the other one of which is incredibly not realistic. The first one is, so imagine this is turbulent water flow. You can imagine most of the viscous dissipation, so most of the heat, is generated in a boundary layer near the edge, so near where you have this solid wall, solid compared to the water at least. And so as a first approximation, you might imagine all the heat going into the ice will just mean that you have a constant melting rate, so constant as in it's uniform all around the boundary, which means you just end up with an extra term in your kinematic condition. So here's the ice flow, the u dot m, and here's a minus m. This is pushing this out, but it's pushing it out at a constant rate. So that's the only change we're doing to our very nice Newtonian Stokes flow problem, for which we could write down exact solutions. Unfortunately, this very slight change, as always happens, means that you can no longer write down large classes of exact solutions for this problem. Just a very small change can completely ruin that nice complex analytic structure. But you can still do linear stability analysis, and you can still do numerical solutions, of course. The linear stability indicates that it's still unstable. It's still unstable to all modes of perturbation. And the numerical is a bit interesting. This is a numerical result using basically boundary integral methods, so they're quite easy to code up, considering that this is Newtonian Stokes flow. What happens, instead of having those outward pointing cusps you do for Newtonian Stokes flow without any melting, is you end up with inward pointing corners. So here I've started with a, if you like, a fourth mode perturbed circle, which is this black dotted line. As it evolves over time, you end up with corners pointing inwards. Whereas if there wasn't any melting, what you'd end up with is cusps pointing outwards at these bits. And that's kind of related to this term here. If you imagine if there wasn't any flow of the ice itself, no Stokes flow, then this is just like normal velocity is constant, which is a problem which you can write down exact solutions to quite easily. It's just a first order PDE. And it's well known to form corners in finite time. Okay, so that was the not very realistic model of melting. I'm going to talk about the very unrealistic model of melting. I'm not sure if the colors have quite turned out. Maybe not. And this is where we're going to say that the heating, instead of being produced in a boundary layer near the edge, is actually produced uniformly throughout the boundary, and then it flows by the heat equation, but because the heat flow acts much faster than the Stokes flow of the ice, we just say it solves Poisson's equation, and there's a Stefan condition on the edge to tell you how much it melts, which means in your kinematic condition, your minus m, if you like, is now minus normal derivative of the temperature T. And this is obviously not very realistic for turbulent flow of water, but I'm interested in it for a couple of reasons. One of which is it's kind of an extreme case. It's an extremely stabilizing sort of melting. The second reason is kind of a bit more indulgent, and that is that you can actually write down some non-trivial, well, one in particular non-trivial exact solution to this problem, which is an ellipse. Again, an ellipse with fixed focal points. And that relates to the fact that this interior problem, if you ignore the Stokes flow for the beginning, for the moment, this interior problem is equivalent to another well-studied problem in 2D viscous free boundary problems, which is Healy-Shaw squeeze flow. If you get two plates with a blob of fluid in between them, say, and you push them together, so you kind of got an apparent mass increase at every point that satisfies Poisson's equation, and your free boundary condition looks like the Stefan condition. And an exact solution to that problem by itself is an ellipse with fixed focal points. So when you stick these two problems together, this exact solution is preserved. And so there's some fun work we can do with this problem. In particular, we can do some linear stability analysis. Well, given the focal points are fixed, one should not resist the urge to write this in elliptic coordinates. I like to think of elliptic coordinates as a conformal transformation affected by the hyperbolic cosine. So here zeta is now another auxiliary variable, and z is my physical variable. And what this does is it maps the plane to a strip in the zeta plane. Outside of the ellipse is, like to the right of this line, psi, which is a real part of zeta, equals S naught, say. I think I've used S naught to mean 2 or 3 different things during this talk. And inside the ellipse is to the left of that line. And the fact that this solution preserves those focal points just means that you can write your solution for the free boundary in terms of an ordinary differential equation for this S naught. So if it expands, this line just moves to the right. If it contracts, it moves to the left. And that will depend on the balance between the pressure pushing it inwards, which is this P infinity term, and the melt rate, or the heat generation, which is that little cube. Okay, but like I said, you can do linear stability on this problem since we now have an exact non-trivial solution. Although it is kind of surprising, I think, that you can actually work out the exact solution to the linearized perturbation problem for this problem, given that the base state is really not that trivial. It's this ellipse in time, but you can actually write down an exact series solution in terms of these little, so S tilde is like my perturbation, so this thing, to the ellipse, in elliptic coordinates. And you can write it down in terms of series, where the terms in the series look like this. What this term in the denominator comes from is it's the square of the scaling factor when you convert to elliptic coordinates. So it's quite important. And I put this only for, that should be k actually. K is greater than or equal to 2. So these are like the kth modes. That should be sk as well. Anyway. Put it like this because actually the first 2 terms in this series involve all the coefficients, all these gamma k's. So this isn't really, these aren't really eigenfunctions of this problem. but these terms certainly tell you about the linear stability with regards to these higher order perturbations. Actually, this solution is also valid even if you have a time-dependent base state. So even if your S0 is a function of time, this is still a valid exact solution for the linearized perturbation problem. Most importantly, I suppose, is that you have an ordinary differential equation for your amplitudes of these perturbations, so d gamma k dt, and this tells you whether these terms are growing or growing or decaying in time, and that'll tell you about the stability of your ellipse to these higher mode perturbations. And it turns out that it is stable, so you would expect to see an ellipse unless your S0 is small. So unless your ellipse is very long and thin, in which case it's not stable, these terms are growing. And you can kind of see from this picture of, I think this is S6 maybe, that it's biggest at the ends. And so you expect when it becomes unstable, it's most unstable at the ends, which is kind of what you expect because that's where the curvature is greatest. And there's a numerical solution showing that. There's a relatively fat ellipse. And it's unstable, so the initial black line is a quite heavily perturbed ellipse, and then it goes to an ellipse, the red line. In this case, the other thing, it starts very close to an ellipse, and then you end up with cusps, I think, end up forming at the ends. Again, it's most unstable at these endpoints, whereas you don't see a lot happening on the roof. Okay, so there's some questions about that. Really, it's not very satisfactory in terms of the melting, and what you'd want to have is a better model of viscous dissipation in turbulent flow. So that's still work we're thinking about. Okay, lastly, I was going to talk about the other issue, which is going from Newtonian flow to a power law fluid. So just to remind you, the ice is really not a Stokes flow, not a Newtonian Stokes flow, it's really this shear thinning flow with an index of about a third. And there's a lot less you can do with this, obviously. You no longer have these nice, complex analytic theory of exact solutions. And the numerics is a lot harder. You can't do boundary integral methods anymore. But I have done at least linear stability. And here's a schematic in case you've forgotten what linear stability looks like. You start with a circle, you perturb it a little bit, and then you solve for the growth or decay of those perturbations. You can imagine this is going to be a much more difficult problem, given you've got this power of a strain rate tensor in there, but you can certainly get a solution in closed form. It looks pretty messy. I do it in Maple because kids these days can't do algebra. What you do is, so say if our perturbation is a kth mode, so cos k theta, and it's growing at a rate ck, so we want to find these ck's. You sub in ansatzes to all your equations, all your flow equations in terms of powers of your radial coordinate r, where you need to solve for these powers. So for instance, this is the radial velocity. You also have one for the other velocity and the pressure. What you end up with is a quartic to solve for these coefficients. So here's some solutions for the second mode. Because we're doing an exterior flow, we only want the ones which are less than 0, so that it's bounded at infinity. Interestingly, what happens is that at a certain point, they stop being real and become complex. So if like this is just the real part, and here this is n equals 1, so this is the Newtonian flow, where they're both real. But once it becomes sufficiently shear thinning, remember ice is like a third, so it's down here. These are actually complex conjugates. It's kind of interesting because it means your correction is actually oscillating backwards in r as well as oscillating in theta. But you can also work out these ck's, so whether your modes are growing or decaying. Turns out they're all growing, so it's still unstable to all perturbations. But now, instead of the Newtonian flow where all those perturbations were growing at the same rate, to this point here, it now depends on your mode. So the more shear thinning you are, which is further down here you are, for lower modes, the less unstable it is. So the black dashed line, this is the k equals 2 mode, so if you like the mode that makes it more elliptical, becomes less unstable, but it's still unstable. And then as your mode number increases, it approaches the Newtonian result. So if like this is non-dimensionalized with regards to that leading order decay of your circle. So the end result is that all modes are unstable, and the higher modes are more unstable than the low ones if you're in a shear thinning regime. But this kind of complex conjugate idea is a bit weird, because what it would mean is you'd end up with, like I said, oscillations going backward in R as well as in theta. And this is this is just a picture of the linearized solution. This isn't a numerical solution or anything. And it's a bit exaggerated, obviously, because the correction is still just infinitesimal compared to the leading order solution, so it may not actually oscillate in reality. But I just put that up there because I thought it looked cool. So maybe you'd see something like that, but maybe you wouldn't. Okay, but with regards to that Newtonian versus non-Newtonian question, I think I'd really like to see some numerical computations to compare to my linear stability to see if this is something that actually happens, because it was certainly something that I didn't expect. And I think I'll stop there.
Questions or comments?
So you presumably tried to do complex variable for your TA model.
So for just the melting on the outside, this one?
Yeah, because I mean, given Stokes and P.D. Shore both have the same classes of solution, not just the differences.
Oh, you mean the one like this one?
Sorry, yeah.
Yeah, the difficulty there is kind of the fact that you're mapping, like one of your mappings is to the outside, one of them is to the inside. And they're often, like only one of those mappings will be rational or elementary in any way, the other one will be incredibly difficult.
Anything else? If not, let's